a little bit about what I didn't have time to talk about in the last lecture, and then leave the applications for the second part of this lecture. So maybe it will be a little bit sketchy for lack of time. I think it's better to, and I couldn't skip the last part of the last lecture. That would be sort of missing the point. But let me just repeat the lesson we learned yesterday, that we were looking at sigma models, where we, starting from the basic structure we had in the first lecture, we're adding geometrical structures or objects, both on the target space and on one sheet. So last time I added fermionic variables on the one sheet, and I was looking for supersymmetries on the one sheet and trying to figure out what kind of geometrical structures I would need on the target space for this to be true. So it turns out that so this is the lesson which maybe got a bit scrambled in the end of the last lecture because of lack of time. So the lesson is that there is no additional requirement if I add plus and minus fermions. So I have a left moving or right moving supersymmetry 1,1 supersymmetry. There is no additional requirement. I will always have that in right fermionic content. So this is always true. But if I add more supersymmetries, if I require more supersymmetries, right? So I have there's a closed tree form also in the general case. So if I add one more supersymmetry in the one of the sectors, this will lead to SKT geometry. That's strong Kähler torsion, and but you could see that if you turn off the H field, you will just get Kähler structure. If you add an extra supersymmetry both in both of the sectors, you get something which I didn't even have time to measure, which is called generalized Kähler geometry, or there's an alternative name called bi-Hermitian geometry. So bi-Hermitian refers to the fact that you have to add one complex structure here, one complex structure for this geometry, and they're both, the metric is Hermitian with respect to both complex structures. So that's the origin of the name. Right, then you can go on and play this game for higher supersymmetries, which I also indicated last time. Now, today I want to reverse the procedure in some sense. So instead of looking for symmetries here and seeing what that gives me, what I need to add here, I'll try to introduce a formalism where the symmetries will be manifest. And then everything will just follow in a simple way. So this procedure, this calculation of 2 is called superspace. And I'm not going to go into any deeper meaning of this. So I'll start with a superspace which has only one supersymmetry. So that's the simplest case, and I'll avoid a lot of just technicalities, which doesn't really change anything on the fundamental issue. So we already looked at that case from the other point of view. Right. So the action which had 1,0 supersymmetry was this action where we just added the plus fragments, no minus fragments. So it was the first case we looked at yesterday. Now this can be rewritten compactly and nicely using this additional coordinate in this way. Oh, this is a Grassmann coordinate. Tell you what this means. So here I define a new operator, which is essentially one of these derivatives, but there's an additional piece. Which is an ordinary space-time derivative. Oh, sorry. This phi now is not the same phi as this. It's this is supposed to be a capital phi. This is supposed to be. Maybe I should change this to make it really explicit. So this is a small phi. So this capital phi now is a function of this additional coordinate as well as the one-sheet coordinates. So it's a combination. Like this, plus, so when I say function, you shouldn't take that too literally. The only dependence you can have on the Grassmann coordinate is a linear term, because since it's Grassmann, theta plus square is 0. So if you think of it as a function, the Taylor's function is the only terms you will have. Okay. So if you try to now use these definitions, we could try to write what this actually means. plus on capital phi is d plus I theta plus d plus on small phi theta plus psi plus like this. And then I just act with the operator. So this derivative kills this, but here there is an psi plus term, and this guy gets me something here, plus I theta plus d plus phi m. But when I hit this term, derivatives can act on psi, but then I get 2 thetas, which is 0. So this is the only thing that's left. So let me now write out the full thing, theta plus. So minus I, this object plus I, theta plus d plus phi m, times the second guy, which is d minus minus on phi m plus theta plus d minus minus psi plus m. So this is now the Lagrangian. And again, acting with this derivative, there's one term which doesn't contain any thetas that drops out. Terms containing one theta will give me some contribution. Right? So there will be a term I d plus plus phi m, d minus minus phi m, theta m, and there will be a term from here, which is so there's a minus I and phi, this stuff, and then there's this term, which is so theta has to anti-commute through here before I can act on the derivative. So there's plus I so no I. So this guy, so it's for the minus I have this. So there's a minus and there's a psi plus and d minus minus psi plus right, and then you take in the i's and the plus. So this is the same action written in this compact way. Now, what did I gain by rewriting it this way? Well, it's now possible to realize the supersymmetry transformations in a very nice way. So I can represent them in terms of another differential operator. So my claim is that if I do a supersymmetry transformation on this superfield big phi, it can be realized. And now I include the parameter epsilon minus, which I had yesterday. By acting with this operator Q on this, we can write it out explicitly to see how this goes. The theta plus minus I plus plus equals Q on which is small phi plus theta plus psi plus minus, so there is this guy acting as psi plus, and this guy acting gives me minus I theta plus d plus phi, and this guy has 2 theta, so it just drops out. So, right, what does this mean? This derivative, if I write it out, so this will be phi theta plus variation psi plus. So now I can just read off what I get. So let me put it here. And so reading, this is a superfield and this is a superfield. So now I can compare components. And I see that the transformation of phi is epsilon minus psi plus, and the transformation on psi plus, the theta component, is epsilon minus I d plus on phi, which are the transformations we have. And so, okay, so it seems to work, but why is this now? Why does this give me the possibility to construct actions which are automatically supersymmetry invariant? Well, so we're writing an action which looks something like this. So this is the numerical. L. So supersymmetry transformation of the action just is I get by acting with this operator Q plus on L. But Q plus and dD theta are the same up to a total space-time derivative. So up to a total space-time derivative, this can be written as there's the minus sign, epsilon minus Q plus squared on L. And Q plus squared, if you compute it, is also a space-time derivative. And, well, assuming we can throw away boundary terms, this is 0. So this formalism, I can put anything here, essentially. And it will be invariant under supersymmetry. So now you don't have to look for supersymmetries in the hard way. You can just construct the areas where this is true automatically. Okay, so the important points here are the supercovariant derivatives, which fulfill anti-commutation relations of this type. You can compute them if you want. and the Q's, which I'm calculating with the D's. And now, I'm going to cheat a little bit, but essentially, if you want to add more supersymmetries, and this was the trivial example, it was easy to do also without using superspace. But now we could think about PQ supersymmetry, where you add an arbitrary number P of supersymmetries of one type and an arbitrary number Q supersymmetries of the other type. And to realize this in a superspace, you would, in principle, have to, for each P, you have to add theta plus coordinate. And for each Q, you have to add theta minus coordinate. And correspondingly, you will get D plus minus operators. So that this, and here's the plus 1 up till D plus P. Here's a D minus 1 up to D minus Q. Power as well. And each of them separately satisfies an algebra of this kind. So, for instance, how would a sigma model in 1,1 superspace look like? Right, so we have now a theta plus and a theta minus, and a D plus and a D minus. And an action would look like d to theta and now I have to differentiate both with respect to theta plus and theta minus. And what could I put here as an L? Well, it should have the correct dimension, and it should have the correct Florence properties.
Rikard,
Yeah.
why are you differentiating and not writing the integral?
Because I didn't want to confuse things by talking about Grassmann integration. Then I would have to do a little bit about what I mean by integrating. So, I mean, for this purpose, it's enough. If I don't want to talk about the meaning of superspace, this is just enough. It just allows me to construct automatically supersymmetry invariant connections.
It's the same, right?
It's the same, yeah. But I just don't want to have that discussion.
The difference is that this forces you to, I mean, you write it as much as you want, it forces you to have these thetas changing in some particular bundles on your curves. So, so now you're telling me that I can put anything in L, but I can't really, because this theta plus is a section of a particular bundle.
Yeah.
Which is hidden under the right here.
Right, so the point, so I said before you can put anything, which is not really true. So one strong constraint on what you put here is that it should have the correct dimension. Because this has dimension, length dimension 2. And these derivatives, well, you can figure out what their dimension should be, because this has dimension -1, so each of them has dimension -1/2. If this is 2 and this is -1, so this has dimension 1, so this should have dimension -1 again. So I need 2 derivatives here. So the natural thing to write here for supersymmetry invariant action with 1,1 supersymmetry is this for the sigma 1. And in fact, now you can do what I did, plug in what these derivatives are, plug in, sorry, I'm cheating a little bit now. The superfields are a little bit more complicated. There are more components because there are more theta, so there are some new ingredients. But essentially, just plug in the definitions, do the derivatives, and you get the sigma model we had before, even if G is not trivial. Right, so this should now be a function of the superfields. Now, if you go up, there's in supersymmetry, there's some new features which should be mentioned because I used them today. So let's say we add the two plus supersymmetries. Then we need two thetas, so there will be two supercovariant derivatives with a plus index and one with a minus. And it turns out it's useful now to, instead of using this real version, you can define complex combinations of those. This and the complex conjugate. And so this is important now because if you start to try to write some action here, and with 3 theta derivatives. So again, dimensional arguments. This is dimension 2. This is now dimension minus 3/2, so this is dimension 1/2. So I need something which contains one supercovariant derivative. So you might try something like this. But if you try now to go to components, you see that you get more than this, the sigma model that you wanted. You get additional terms that you don't really want to be there. But now when we have enough room in the superspace to impose constraints on the superfields. So first, instead of having real superfields, we assume that they are complex and that the phi's are annihilated by d bar, and the phi bars are annihilated by d. And such superfields are called chiral. And in fact, this is this projects out the stuff we didn't want in the action and leaves something which agrees again with the action we were working with yesterday. Okay, so this is one feature that's important in higher superspaces, that you need to work with not the full superspace but some subspace, some invariant subspace of the superspace, so something like chiral, some other type of projection, and then even when you get up even higher, you get even more possibilities. Here there's just this possibility. Another thing which I wanted to point out here
I'm sorry.
Yeah.
I'm sorry, but I don't understand why you need to impose constraint. Can you?
Well, if I, so a very prosaic way of saying it is I take this, I try to figure out what it contains in the same way I did, well, I already erased it, but in this very simple case, I just worked with did the differential, the operators everywhere, wrote out all the components, and I can figure out what this really means in terms of an ordinary field theory, in ordinary space. And if I do this here without imposing the constraints, I find that I get more terms than I want. Okay. For instance, I'll get the terms actually tells you that this has to be 0, which is not very nice. So to get the right physical content of the theory, I need to impose these potentials. Yeah, so another thing that I wanted to point out here that, well, here there is something in, this we know what it is. It's the metric on the target manifold, and we could also add the B field here if you want to. But here there's something funny appearing. It looks like a one form, right? So there's some one form on M, not necessarily globally defined, but that contains the information about G and B, or G and H, the real geometrical structures that we have on your target manifold. So you could say that lambda is a potential for the geometry. And this is something that also repeats itself when we go up into to more and more supersymmetry. That the Lagrangian itself is a potential for the geometry. It's a simpler object that, taking derivatives of it, you get all the geometrical information that you need. So this tells us that a sort of slightly less known fact. We all know that for Kähler geometry, there is a potential. You can find a function such that when you take, depending on the complex coordinates, you take derivatives of this function, you get the metric. Here's a slightly less known fact that if you talk about SKT geometry, there is always a one form potential. It's similar to the Kähler potential in Kähler geometry. Right. Okay, so now let me get to today's topic. This was yesterday, and let me talk about an application of this. Place where you can use this formalism to find interesting new results. So, I mean, the point is that if I write things in this way, I automatically keep the supersymmetry. I just have to make sure that everything can be written in this way, and supersymmetry will be there. So, in particular, I can perform manipulations here. I can gauge this model or do other things. As long as I respect the supersymmetry, the target space geometry of the result will have the correct geometrical properties. So that means that I can try to look for new manifolds of the particular type that is connected to the particular flavor of supersymmetry I have by manipulating the action in different ways, keeping the supersymmetry. So to do that, let me just show you in a very simple way what I mean. So what I want to do is a supersymmetric version of quotients. Okay, what's a quotient? So let G be a Lie group. Compact Lie group. That acts on correct manifold M. So, in general, the action of G on M could be pretty wild, but let's assume that the G acts freely, so there are no fixed points. So then M gets the structure of a principal G bundle. And the base manifold is M over J. So the base manifold is the quotient of M with respect to the Lie group. Okay, so this is the structure I want to do, but using the supersymmetry. So the point is that I have more information on M. It's not enough to just reduce by G, because I have geometrical structures on M that I want to preserve. We know that the target space geometry is connected to all these geometrical structures that we had on them. So if I want to do this, preserving the properties of the target manifold, these new objects, I have to define new objects on that reduced manifold, which would have satisfy the same properties. Metric should be Hermitian, so on and so forth. Right. So the simplest case is if you just have a metric. Right. So then you have to say something additional about how. Well, okay. Too many big G's. Okay. Big G now is the big G, the smaller metric is small G. So you have to say something about how G acts such that, not for any action of G we can preserve the properties of the metric. So the Lie group should act as a symmetry group. It means that you have your M, your G, and something like this, and there's the M over G base manifold. And if G acts as an isometry, so essentially what it says that is the metric doesn't change along the fiber, which makes it plausible that you can define uniquely a metric downstairs, independent of for the whole fiber, so to speak. Right, so the way you do this is that you define a horizontal subspace. The vertical subspace is the tangent space. To define a horizontal subspace, you have to define in some particular way. So any vector on the base manifold can be lifted unique into a vector in the horizontal subspace of M. Let's call it XH. And then the quotient metric is defined as the metric on the lift of the vector. Okay, you can show that, let's say, by the point you choose on the fragments. Okay. So if you wanted to realize this setting using a sigma model, so far we don't need supersymmetry because we don't have all the extra structure, just the G. So we can talk about the simpler case with the bosonic sigma model. So we know now that the Lie group acts as isometry, so that means that there are isometries here, which means, as we saw in the first lecture, that there is a symmetry of the sigma model. So this symmetry we can try and gauge this symmetry to create a new sigma model that would be invariant or independent of these directions. So gauging is a way of gauge degrees of freedom are not really there, so it's a way of getting rid of degrees of freedom, so to speak, morally speaking. Now, of course, this is something that you have to be a bit careful about. There's a long and beautiful story about when symmetries can be gauged and not gauged, which I wanted to talk about in the first lecture, but I didn't have time. So anyway, let's assume that this symmetry can be gauged, and if I'm assuming it's a U1, then there's no problem. So the gauging in general is done. It's done by introducing a gauge field. where connection on the worksheet, I'm not introducing any kinetic term for this field because I don't want to treat it as a dynamical field. I want to treat it as a field. The role of this field is to get rid of the dependence in this direction. So,
And Ka is
yeah,
the
oh,
basis.
sorry, yeah, this is Ka is the K vector. Ka. So yeah, I use the indices, so let's put the indices back arbitrary coordinates. So the model looks like this now. G and M. And since I didn't put in the kinetic term for A is a Lagrange multiplier, essentially. It can be integrated out, it doesn't have any dynamics. The equations of motion can be solved. In this case, this is a U1. Let's put it full. So this now looks like R, A, B, A, B, if I define this connection on the target space, so A, mu A is just B root phi and A, and R, A, B is inverse of R, A, B is A, and G, and so these are just some formulas, but if you actually look at what they mean, this is a connection one form on the target space manifold. And if you look at the kernel of this connection one form, well, it's a connection on this principal bundle, and the kernel is the horizontal stop space that we were talking about before. So plugging this in the solution back into the sigma model, the sigma model here, we find a new sigma model that lives on the subspace with the correct metric, the same one that we got from this construction, choosing the horizontal subspace. Okay, so this is the sort of basic construction, and now what happens when you have more structure? What happens, for instance, if your manifold is a Kähler manifold and you want to keep the Kähler structure? That means well, you have an I, and you have a G, and you want to reduce them in such a way that in the reduced manifold, there's a new Kähler structure given by this Kähler structure. Okay, so of course you can figure this out in the hard way, but superspace, if you use the formalism I introduced this morning, will tell you how to do it. So Kähler-Geometry is, as we know now, is associated with 2,2 supersymmetry and no 3-form. So if we use a 2,2 superspace, will look something like this, where K is the Kähler potential for this Kähler manifold. And let me do a very simple Kähler manifold, flat space. For instance, flat space has many isometries that can be gauged, and my claim is that if I do this in 2,2 superspace, the result will be the Kähler manifold. So here's an isometry. And the complex conjugate, the superfields transform into complex conjugate transformation. So they both have the same charge under a U1 group. So how do we gauge in superspace? Right? Gauge means that we make the symmetry local. But this has to be a function, but the function is not something supersymmetric. It has to be a superfield. Lambda constant goes to lambda chiral superfield. And the reason why I have to choose it to be chiral is that phi is chiral, so I don't want to switch, I don't want to mess up the chirality properties of phi. So lambda has also has to be a restricted superfield, or constrained superfield. Now the problem is, the way to see that this is not a local symmetry, it's a global symmetry, is that now I have a symmetry, well, the transformation is the number phi I, but then phi 1 bar, that before transformed with the e to the minus I lambda, now we transform with the minus I, the lambda bar. The lambda bar is an anti-chiral superfield. So e to the minus I lambda e to the minus I lambda bar is not 1. Okay, so then this is not, when I make it local, the action is not invariant anymore, which is as it should be. So now we need to make it local again. We need this to be an invariance or symmetry, and then we gauge things. So we introduce a new superfield. And it's a real unconstrained superfield. V such that e to the v transforms into minus I lambda into the v I lambda. And it needs to be unconstrained because otherwise any constraints will be violated by this transformation properties where we have chiral and an anti-chiral field. Okay, so the gauging now looks like the gauged action. Looks like this. So phi 1 bar, phi 2 bar, e to the v. And in fact, there's one more term you can include because the gauge group is U1. So you'll see that, full measure here, D2 sine, D4 theta 4. C is the constant. But if you look at the gauge transformation properties of such a term, you will get out the phi character, a term which contains only chiral fields, a term which contains only anti-chiral fields, and those terms will be killed by the measure. So this, a term like this is also a gauge invariant. So let's put this in. The V field is unconstrained and can be integrated out.
So it's the same V.
This is the same V.
Okay, and it transforms.
The V transforms in this way. Right? So this is U1, so there's no problem here. I can rewrite this as V minus I lambda plus I lambda bar. Right? So delta V is minus I lambda plus I. Okay. So integrate out V. So equations of motion looks like this: phi1 squared, phi2 squared, e to the v is equal to c. E to the v is
It's a non-linear action. How can you integrate out?
Pardon?
How can you integrate out V? It's a non-linear action.
I take the variation with respect to v.
You don't integrate. It's just a critical
I find the equations of motion of v. Right, that's what I solved the equations of motion of
You
v.
do the classical, so you don't do the quantum.
Well, there's no derivatives here.
You can do
It's not
the
a propagating field.
I see.
So even quantum mechanically, this works.
Why then? I mean,
no, you can do it quantum. I mean, either you do this trick, which is enough for geometry, or you can do like Witten did. You add a kinetic term, let the model run, and in infrared, I mean, basically, effectively, it will be like integrating this field. That was the argument. But you can do it even at quantum mechanical level. If you add a kinetic term for V, then the statement is that what Rikard will get now, it will be the infrared limit of the theory.
so I see that there is no kinetic term in V, but there is also no kinetic term in phi if I just look at this formula. So what is the difference? How is it that you don't have any kinetic term?
No, for geometry you don't need it. So, I mean, if you discuss quotients, what Rikard is doing is fine. Now, if you want to repeat this dynamically, then you...
There is a kinetic term, you find it out of the fields.
Right. But, he doesn't...
There's no kinetic terms for V.
Is that true?
Yeah. This section doesn't contain any.
It's a background field in this section, but I'm trying to say that there is either you do these things and you get the geometry, or you can introduce kinetic term and do the proper physics and get the same result. So,
Okay, so yeah, there's a more consistent way of doing things. But if you're more happy in this way, let's say we're just doing geometry. We're not interested in any quantum aspect. We're interested in constructing a new Kähler manifold from an old Kähler manifold, using this formalism where the supersymmetry is manifest. And that's all I need for the Kähler property to be correct. Then you could start asking quantum questions, but that's not what I want to do today. Right, so e to the v is this, and when you plug it back, you see this term is just a constant, and here you'll get, one constant term, but the action will be e to psi d4 theta, there's a c, and there's a log phi1 squared plus phi2 squared. And you can use now that the action is gauge invariant, that is invariant under these transformations, to gauge away one of the fields. So you get a model which depends only on one current field. Let's call it just phi. Instead of two, you lose two or one complex dimension of your target space manifold. There's only one coordinate now. This is now a Kähler potential for the new manifold, Kähler potential. And you know this Kähler potential is the Kähler potential for the Stony-Metric on CP1. So this is a procedure that gives me a new Kähler manifold, CP1, from an old Kähler manifold flat space by going through this route where you keep supersymmetry manifest at all points. Now,
so is lambda complex in some way?
Lambda is a complex field. You mean this one?
Yeah, so it's
Yeah, it becomes complex, yes.
It's not U1.
Yeah, that's a good point. Yeah. So there are different ways of looking at this quotient now. You can now say, how was the simple picture when I just reduced the metric modified for this to be true? Now, how did it work? So of course, mathematicians know how it works because they know Kähler quotients. You can define it without thinking about superspace. But you can use the superspace and take it apart and see what I had to add to make the quotient work. So there are two ways of looking at it. So if I'm looking at it from the point of view of n equal 2,2 superspace, what I did was complexify the action of the gauge group and then quotient. But you can also go down to 1,1 superspace and look what I had to add, what I added when I gauged it. Yeah. So to go down to 1,1, I have to do two of the derivatives here. Keep two of the derivatives and do two of the derivatives. If I do that, V contains gauge fields and a real scalar field. Sorry, bad name. And if I look at the equations of motion of F, gives me a condition 1 squared plus 2 squared is equal to C. So, integrating out F, V was not just doing the quotient by the gauge group. It was first imposing a constraint, telling me that I have to look at the hypersurface inside my manifold, which is given by this equation. And then I get the picture I had before using the connections plus and minus. Right, so the picture is a little bit more complicated now. And so the M looks like this. Now there's a hypersurface inside M. Where phi 1 squared plus phi 2 squared is equal to C, and the gauge group G acts inside this hypersurface, and then I can repeat the trick before that, and I take the quotient of this hypersurface with G to get CP1. Yeah. So it's a bit more intricate, but this is essentially the Kähler quotient as described in the mathematics literature, but discovered using superspace, which is not the way it happened. Yeah. So yeah, let me stop there. I think I don't want to complicate it.
So, any questions for Rikard?
So the rejection has to be free all the time. This example is C2 modulo C star, right? So then it's the origin of it.
Yeah, the origin is that exactly. So there's good point. So I said that the action should be free, no fixed points, but here there is a fixed point. But actually, I wasn't doing the quotient in the way I presented it before. What I need now is that the action on this surface is free. If I choose C to be not equal to 0, I avoid the fixed point. Right? The fixed point is phi 1 equal to phi 2 is equal to 0, but if C is not equal to 0, I avoid this point. So the action is actually nice on this hypersurface, which is what I need. And this is what I wanted to tell also. So the words that you hear in the usual description is that this is the zero level surface of the moment. So if you do the Kähler quotient in the usual way, you look at the symplectic form. The symplectic form together with the isometry gives you a moment map, which then that shows that the action of G is inside on the surface of the level surface of the moment map. That's the so here I can relax this condition that G acts without fixed points a little bit because it doesn't have to. They could be fixed points, but they have to be away from the local.
And it could be resolved anyway. Hopefully, the fixed point can be resolved. Because if there's no fire, you always turn that.
Yeah, but this is a fire that was
Yes,
That's what I agree.
Any? Yeah.
So I'm not sure if I understood the gauging procedure. Let me just check. So you had a super source, super worksheet. You were mapping to this hem that you put some geometrical structure. This is just a metric. And then the action was essentially the area of the image. And now you want to turn on an action of G on this target. And somehow I want to get an action for the same model to target the quotient. And is it the gauging the same thing as just adding a trivial bundle over the source and now looking at equivariant maps from this trivial bundle into your original manifold M, equivariance by the action of G on both sides? This sounds to me that this adds at least it adds the same fields that you're just adding.
Why do you need a bundle to be trivial?
Sorry?
Why do you want the bundle
Well,
to be
your
trivial?
fields are just connections.
Yeah.
Right, so you're not adding any to non-trivial topology on the worksheet anyway. So.
That's true, but yeah. Well, eventually there has to be an identification with the connections I have in the worksheet and a connection on the space-time.
Yeah, so I think this is just the fact that you're looking at equivariant maps from this bundle on the worksheet. I mean, I bet you could add any bundle on the worksheet, but I wonder if these two procedures are the same. I mean, this way I'm writing you an action on the quotient. And I wonder if this action, I'm writing you an action without writing any coordinates or any equations. So I wonder if this action is the same as the one that you wrote. Even in this case too, it seems to be that I'm getting the same answer. Or GM action on C2.
It sounds plausible, but yeah, I will have to look at it more carefully.
Any other questions? If not, let's thank Rikard. So we meet 11:40.